All right, this will be a quick mechanical introduction to the definite integral, section 7.6. You're free to read section 7.6 if you want an overview as to what we're doing. It might be best preceded by section 7.5. In short, the definite integral is the calculus method for finding net signed area under the curve. And we've already done net signed area, but we haven't done net signed area where the region has a shape that can't be found by Euclidean geometry formulas. So just like a general curved irregular shape, how do you find the net signed area? Everything else about the net signed area that we've learned still applies, but the definite integral is the calculus way of finding net signed area. So let's title this 7.6, the definite integral. And I'm just going to take the examples from the book and give you a step-by-step overview of how to deal with it mechanically. There are a couple lectures awaiting us on how this works theoretically and conceptually, but mechanically is what I'm after for tomorrow. So example 1 from section 7.6 looks like this. Integral 1 to 2 x dx. First thing you'll notice are the little numbers called the lower limit of integration, and as expected, the upper limit. Right there. All right, so quick antiderivative on this. After all the work we've done, we're experts at this right now. And from this point in the anti-differentiation, we add this evaluated at bar, 2 and 1 in that place. And what that translates to as you continue the evaluation is 1/2 2 squared minus 1/2 1 squared. And that equals what? What's that? 1/2 times 4 is 2. 2 minus 1/2 is 1.5, call it 3/2, and we're good. So the takeaways from this quick introduction is the lower limit, the upper limit, and how that applies here in this evaluated at notation. So you could make yourself a little formula or something to remind you of how that works. So maybe x evaluated at b and a, maybe it's better to do f of x. There we go. And that equals f of b minus f of a. Subtraction is called for in the formula defined by this evaluated at when we have two limits, an upper and a lower. Continuing with example 2 from section 7.6, we have integral 0 to 3 9 minus x squared dx. All right, same process, first order business, anti-differentiate. We should be able to do that with one brain tied behind our backs. 9x minus 1/3 x cubed. And I'm just going to put that in parentheses because that's the entire antiderivative, evaluated at 3 and then at 0, and that equals the evaluation at 3. So let's see if I can be overly explanatory here. 9x minus 1/3 x cubed evaluated at 3 minus 9x minus 1/3 x cubed, evaluated at 0. So you just have to be careful, mind your subtraction, etc. So plug in 3, what do I have? 27 minus 1/3 times 27. That's all that minus, that's just 0, easy peasy. I get 18, life is good. So again, keeping in mind where this is going, 18 is the net signed area. Let me highlight this. 18 is the net signed area under this function, 9 minus x squared, on the interval 0 to 3. That's how every piece of this plays out graphically and how the definite integral connects to net signed area. All right, a trigonometric example, that'll be fun. Next slide. All right, example 3, nice and straightforward. I have integral 0 to pi cosine x dx equals, anti-differentiate, I get sine x, evaluate that at pi and 0, I get sine of pi minus sine of 0, and that gives me 0. So the net signed area underneath f of x equals cosine x on the interval 0 to pi, net signed area, excuse me, is 0. If we remember what cosine looks like, he says optimistically, on 0 to pi. So that's pi over 2, and that's pi, and that's 1 and negative 1. Kind of looks like this comes off here and like that. And as we know from net signed area, it appears as though we have symmetrical, though opposite signed area regions, caution not drawn to scale, split right in the middle by the interval. So it's pretty clear that the net signed area is 0. Good. One last example. Next slide. All right, this one's example 5, part 2. And again, you can tell I'm just doing the same thing, anti-differentiate, evaluate the antiderivative at the upper limit, and subtract from that the evaluation of the antiderivative at the lower limit. The only thing that can change is the complexity of the anti-differentiation. Oh, excuse me, 1 to 2, 1 over x dx equals, anti-differentiate, ln x, I don't need the absolute value because I know I'm only plugging in 1 and 2, so I'm going to go 2 to 1, that equals ln 2 minus ln 1, and that equals ln 2. Done. You know because that is equal to 0. All right, easy peasy. I'll get a practice sheet together and have that for you in class tomorrow. I know I said free study. I lied. Signing out.